So to celebrate Pi Day, I would like to talk about one of my favorite topics. And for experts in the room, believe it or not, I'm not going to be talking about partitions. I'm going to be talking about a subject that we all learn from a very early age, just basic numbers and the distribution of primes. So this lecture is called the Riemann hypothesis. Let me just dispel, make sure no rumors get started. There will be no announcement about the proof of the Riemann hypothesis. So feel free to leave now. Peter wants to get up and go. I think we will have something interesting that I can offer you at the end that sheds some light on how to think about these problems. But this lecture is really about what is the Riemann hypothesis and why do we, as number theorists, care so much about it. So if you want to win $1 million, I recommend that you think about the Riemann hypothesis because it can be really hard to win $1 million. So I stole this image from the internet. I presume it's from the television show Who Wants to Be a Millionaire? And there are some easy questions that could help you win $1 million. For example, which of the following is the largest? A peanut, the moon, an elephant, or a kettle? All right, so I actually cut off the top of the face because, yeah, that wouldn't be very good. My name would be mud with someone. And it can be really hard to win $1 million because about 18 years ago, a collection of mathematics problems called the Millennial prize problems were proposed. And each of them comes with a bounty of $1 million. And this lecture is about the fourth problem, the Riemann hypothesis. There are many problems that I think are quite well known, and this lecture happens to be about the fourth one. As probably most of you know, the Poincare conjecture has now been solved, but apart from that, I think these problems are all worth thinking about. And they're all very important for very different reasons. So in terms of some history, the story of the Riemann hypothesis has lots of interesting stories associated with it. So here's one of my favorite mathematicians. It's an image of G.H. Hardy, one of the very few images that exist. And Hardy has a very famous quote. There's a very famous story about Hardy in relation to the Riemann hypothesis. And it goes like this. Hardy, once on a trip to Denmark, sent a postcard to his good friend Harold Bohr. And on this postcard, he wrote, "Have proof of RH." Postcard too short for proof. So there's not very much else that has to be said, but if you don't know, let me tell you the story. What was Hardy thinking? Hardy had this, long, lifelong battle with God, and his idea was that God would not let the boat sink on the return journey and give him the same fame that Fermat had achieved with his last theorem. Here's another very, very well-known quote. This is another one of our most important historical figures in mathematics. This is an image of David Hilbert. And this is a famous question that he raised. If I were to, well, this hasn't happened yet. If I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven? We have a long way to go. We're not even halfway there, but this is some of the lore that goes along with the Riemann hypothesis. So what is the Riemann hypothesis? It was postulated in 1859. Here's one of the few pictures I know of Riemann. And stated verbatim, it's that the non-trivial zeros of the Riemann zeta function should have real part equal to 1/2. And that's it. There you go. So the talk isn't quite over yet. So part of this talk will be to explain why that matters, what the zeta function is, and tell a lot of stories along the way. So what does that mean, and why does it matter? It turns out it matters for many reasons. Almost everything I'm going to say in this talk is a prototype, a special case of a much larger theory of what we call L functions. And there are big theories that are being developed. You may know about the words Langland's program, Birchon-Swinnerton-Dyer conjecture, and other things. And it's one thing I have to say, in case I forget to say that, is that a lot of those cutting-edge theories have their origins in some of the things that I'm going to talk about today with respect to the zeta function. So Riemann posed his famous hypothesis because he wanted to study prime numbers. So here's a definition. A prime is a natural number greater than 1 with no positive divisors other than 1 in itself. And here's a theorem. It's one of my favorite theorems. I teach it in Introduction to Proofs class at Emory almost on day 1. It's the fundamental theorem of arithmetic, and it's the statement that every positive integer greater than 1 factors uniquely up to reordering as a product of primes. So 6 is 2 times 3, and as we all know, that's kind of the end of the story. However, if you start to delve into other areas of number theory, a field called algebraic number theory, I regret to inform you it's not so simple. But for us today, we will be content with studying the distribution of primes. And the primes are an infinite sequence of numbers that begin with these terms, 2, 3, 5, 7, so on and so forth. I shouldn't have said that it's an infinite sequence of primes yet, because that's like the first question you would ask. Are there infinitely many primes? But before I get that, I would be remiss if I didn't recite one of my favorite quotes about the prime numbers. Primes are ordinary. At the end of this lecture, I'm going to discuss some joint work. One of my co-authors, who's actually not very good at being the co-author part, my friend Don Zagier, has a very famous quote about primes, and it goes as follows. Primes grow like weeds, seeming to obey no other law than that of chance. Nobody can predict where the next one will sprout. There's another part to this quote. But primes are even more astounding, for they exhibit stunning regularity. There are laws governing their behavior, and they obey these laws with almost military precision. The two parts of those quotes seem to be in contradiction. But that is not the case. And part of what I want to do is explain how these two quotes, these two parts of this one quote, come together and begin to illustrate what's so beautiful about this function called the Riemann zeta function that Riemann defined in the 19th century. So there is a very simple algorithm for listing primes up to a given bound. So let me just recall it for you to remind you that primes have been studied for, well, since antiquity. There's the famous sieve of Eratosthenes. Here's an image of Eratosthenes. And a picture basically illustrates an algorithm for listing the primes up to a given bound. Here's this picture. The numbers that are boxed, they are the primes, 2, 3, 5, 7, all the way up to 47. And the way that these numbers are obtained is by first listing the numbers 1 through 50, if you have the patience to do that. You recognize that 1 isn't prime. After 2, you strike out all the even numbers, leaving 2. You notice the next number 3 is prime because you haven't struck it out, but then you strike out all the multiples of 3 there on after. Then you discover that the next number after 3 that has not yet been struck out is 5, so on and so forth. And this method allows you to fairly rapidly list algorithmically the primes up to some bound. But it's not so useful. It doesn't really reveal much about primes. It's a process. It's an algorithm. And if we want to know some of the deepest things about how primes are distributed, although there's a beautiful and deep, rich theory in analytic number theory based on ideas like this, it's called sieve theory, we need a little bit more. So the first clue to this, believe it or not, actually is in the famous theorem of Euclid, that there are indeed infinitely many primes. And this is a great theorem. I like to teach this theorem at Emory in my Introduction to Proofs class because it's a proof that everyone gets, and it's immediately a proof you can criticize because you can begin to ask questions about what the proof does not reveal. It's actually very interesting, really. What was Euclid's proof that there are infinitely many primes? This is not my typing. I cut and pasted after copying this from Google somewhere. But the proof goes like this. It's famous. Suppose that there are only finitely many primes, and let's order them. P1 equals 2, P2 equals 3, all the way up through PR. PR, I am going to declare, is the last prime. There are exactly R primes. What you could do then is define this number capital P to be the product of this complete list of R primes and add 1. And because we have the fundamental theorem of arithmetic, that number cannot be prime, so it's going to be divisible by primes. But that's not okay, because that number, that alleged prime that would divide this, would have to divide into 1, and that's just not okay. There's a lot that you can do with this in a beginning introduction to proofs class. You can compute some of the first few numbers of the form, the product of the first R primes plus 1, and ask students, are these numbers always prime? When aren't they prime? And it's a very good set of exercises that you can assemble that, that I enjoy giving. All right. So if we fast forward a little bit to Euler, this is where the story really starts. You see, Euler, and this is a device that appears almost in every lecture here at this conference. There's a conference going on this week on string theory and moonshine and number theory. We find that we can't escape something called the geometric series, which you learn about first in calculus. If R is a real number with absolute value no greater than 1, then the geometric series in R, summing up 1 plus R squared off to infinity, can be more conveniently written as 1 divided by 1 minus R. This kind of identity is very useful because it allows us to express two kinds of quantities in many different forms, where one side is useful to us and the other side is actually calculable. So just by making use of this geometric series, you can write down some strange infinite series expressions, which maybe don't seem so strange, but humor me. Here in this box, we have some perfectly good ordinary rational numbers, 2, 3, 15/4, and 35/8, which most of us would agree should be written in those forms. But what if you didn't want to write in those forms? What if we lived in a universe where the right way to write 2 was to write it as the sum of reciprocals of powers of 2? If you were in high school calculus, you probably would have objected, but it's something that you would have liked. Maybe. Certainly 35/8 is already almost an objectionable fraction. Certainly you probably don't want to write 35/8 as a product of rational expressions like this. The point being, these intermediate expressions are all of the form that appear on the right-hand side of the geometric series. And if you formally write them out as a product, you realize by the fundamental theorem of arithmetic, all we are doing is summing up the reciprocals of positive integers, in the first case, which are powers of 2, in the second case, which are just products of 2s and 3s, and in this last case, the sum of reciprocals of those integers that aren't divisible by any prime larger than 7. So I think most people would agree 35/8 is something you can wrap your mind around. This is something you might not want to write down, but that's the kind of thing that we want to do here. So this is Euler's idea. And using the fundamental theorem of arithmetic, all I've said is that if we sum up the reciprocals of the positive integers n, summation 1 over n to the s, formally I can describe that as a product over primes. Now we know there's infinitely many of them. And what is it an infinite product of? These rational numbers, 1 divided by 1 minus 1 over p to the s, when we choose s to be a nice ordinary integer. Now today is pi day, so most of the mathematicians in the room can probably guess what's coming next. But now you know what's coming next because I said today is pi day. So there's some very, very beautiful formulas in the spirit of today that relate these expressions with pi. So for example, if you let s be 2, so on the left-hand side that would be the same as summing up the reciprocals of the squares. This expression is a famous expression for pi squared over 6. And it's very well known that if you replace s by any positive even integer, where you're summing up reciprocals of 4th powers or 6th powers, so on and so forth, that there are similar expressions where on the right-hand side you get the corresponding even power of pi times some rational number, which is very interesting in mathematics. And in fact, that's the beginning of many different kinds of mathematics, many with very fancy names. So let's revisit Euclid's proof on the infinite infinitude of the number of primes, and let's not try to be good at it. But let's see if we can get some mileage out of this infinite product just to get a sense of why it's a good idea. So here's an elementary theorem, so please don't be impressed by it, but it's a good step. So in this lecture, pi of x will denote the number of primes less than or equal to x, so pi of n is the number of primes up to n. And let's just sketch a proof of a theorem. Let's show that pi of n grows at least as quickly as the natural log of n. So what I'm actually going to prove is that pi of n is greater than -1 plus a natural log of n, but it's a good exercise to go through to illustrate Euler's ideas. You see, the idea is that we want to somehow access the number of primes up to a large number x by making use of Euler's function. So what's one trick for doing that? So here's an elementary exercise that we could go through. So as before, let's list the primes in order. P1 is 2, the first prime. P2 is 3, the second prime. P3 is 5, that's the third prime. Let's let them be the primes in order. And because the primes aren't as common as just counting 1, 2, 3 up to infinity, it's very obvious that the jth prime is at least as large as j plus 1. Right? Not every number is prime. So I'm throwing away a lot of information there, but let me just pretend that that's like an idea. And you'll see that I've actually thrown away a lot, but I'm going to get a lot out of that. So calculus tells us that the natural log of n is a definite integral from 1 to n of 1 over x dx. And calculus also tells us that we can estimate this integral. And we can estimate this integral by making use of the idea that definite integrals give you areas bounded by curves. So if I want to draw a picture of what the natural log of n is, this is what that picture would be. And your high school calculus teacher will tell you about the theory of Riemann sums, how appropriate. And what you can see is that you can estimate from above this integral by adding up a bunch of rectangles whose heights are, in order, the sums of reciprocals of the positive integers. So of course, from this picture, it follows the natural log of n is bounded from above by the sum of the reciprocals up to n. And if we make use of Euler's idea, where we just declare that pi of n is equal to k, the last prime up to n will be the kth prime. Then all the integers up to n, none of them will be divisible by any primes larger than the kth prime. And so Euler's idea tells us that the natural log of n is bounded from above by this strange expression, despite the fact I've thrown away a lot of information. Now, what we want to do in number theory is we want to take ideas like this, and this is not the best way to do it, as we'll see in a moment. Riemann gives us the best idea. But even right here, the idea is how do we access the number k from these expressions? And this is where it was easy. So when I said earlier that the jth prime is at least as large as j plus 1, I can replace the jth prime as a proxy in terms of this bound by j plus 1. And just with a little bit of algebra, we get then that the natural log of n must be bounded by this product. I no longer have to write down p sub anything because I'm throwing away information. I'm trying to access that k. And if I write that in a slightly smarter way, 1 plus 1 over j is j plus 1 over j. And if you multiply that out from j equals 1 to k, you get a telescoping product. And so by this telescoping, you find the natural log of n is less than something like this. Lots of stuff cancels. Out comes this k. Well, all right, I'm very happy. So I'm not being smart. I just wanted to cleverly, this is not my idea, right? This is a standard trick. I want to access k, but k is what I declared to be the last prime up to n. So that's pi of n. And so I've concluded that pi of n is at least -1 plus the natural log of n. So just by throwing away a little of information and using Euler's idea that summing up the reciprocals of integers can be expressed as a product, I have a way of relating analytic functions, or just the natural log function, to my prime counting function in it. So I've gotten something almost for free. All right. So now let's fast forward a few decades to Gauss. Gauss, and I don't know if I'm going to get this story right, but as a teenager, Gauss invented a lot of great mathematics. In fact, Shamit and I are going to write a paper, I guess, about how he proved that black holes in K3 slash T cross T2 form abelian groups using Gauss's ideas. Stay tuned. But Gauss, while studying tables of primes, made an astonishing discovery. So remember, pi of x is the number of primes up to x. So just to remind you, so what would pi of 6 be? Pi of 6 would be 3 because there's 3 primes up to 6. If you assemble a table of pi of x, say for x being the first few powers of 10, you get these numbers. And if you compare them with the numbers on the right, x divided by the natural log of x, you get these numbers. And he noticed that these columns are quite similar. He didn't actually describe this in this way, but what came to be known as Gauss's conjecture is more or less something like this. If we consider the function lie of x, this modified logarithmic integral, you integrate from 2 to x, 1 over log t dt, right, prime start at 2. And Gauss's conjecture, based on numerics that he did as a teenager, is that the prime counting function should be asymptotic to lie of x, which is in turn asymptotic to x over log x. What does the tilde mean? What it means is that if I were to take either of these two expressions and divide them into pi of x and plug in larger and larger values for x, the numbers I'd get out tend to 1. Actually, the task of doing that is actually very interesting. So if you're a student and you want to calculate primes and compare this function with the actual number of primes up to x offered by, and compare them with what Gauss conjectures, you'll begin to see some patterns, and you might be retracing some of the observations that many distinguished analytic number theorists have done before you. It's actually a very beautiful thing to do. I will show you a graph in a moment that illustrates things that offer glimpses of that. So this is where Riemann enters the picture. He wanted to study Gauss's conjecture. He wanted to prove Gauss's conjecture. And Riemann only wrote one paper in the subject. It's probably the most important paper of 8 pages in length, certainly in analytic number theory ever written, I think. And this paper is actually totally available online. If you go to the Wikipedia page, I think for the Riemann hypothesis, you can click and actually see all 8 pages of this paper. So I did that, and then I cut and pasted images that you can find that are from this paper. So in particular, here it is, 1859. I don't read German, but it says something like, on the number of primes less than a given large number, published in November of 1859. And halfway down that first page, you will find this picture, this function, this expression that Euler understood the importance of, that I've already made use of formally. And what Riemann wanted to do is turn this into a function in S, where S is actually a complex variable, because he understood that if you wanted to make real progress on the prime number theorem, Gauss's conjecture, probably what you would have to do is understand this function a whole lot better. So what's in this 8-page paper? He defined the zeta function. He determined many of its basic properties. And of course, he posed the Riemann hypothesis, that very strange statement I started this lecture with, the statement that this function has the property that its non-trivial zeros have real part of s equals a half, something that doesn't seem so friendly. And as we now understand, it really is not a very friendly thing. But most importantly, the point of this paper was that it offered a strategy for proving Gauss's conjecture, and this strategy has percolated through modern number theory in many, many, many different forms. So what are some of the facts? What are some of the basic properties of this function? As you can see, there will be 4 of them. And as you'll also see, I'm not very good at PowerPoint, so let me just do it anyway. All right. So the zeta function for real part of s greater than 1, we are just going to declare is given by this infinite sum, 1 over n to the s. This is the range of convergence. We're very happy with that, and so this is the starting point. This function has what's called an analytic continuation to the complex plane. I always don't like that because it doesn't mean it is analytic everywhere. This function has a pole at s equals 1, but apart from that pole, in terms of the calculus of complex numbers, this function is about as well behaved as you would want the function to be. This analytic continuation is derived in a very awkward way. It's derived in terms of what's called the integral representation of this function. If I were to show that to you, I'm sure you'll probably find that objectionable. So let me just say that the conclusion from this integral representation is that the zeta function, zeta of s, has a remarkable symmetry property. Its values at s reflect its values at 1 minus s if you're willing to work with these multiplicative factors. And among other things, because of the presence of this gamma is the ordinary complex gamma function, and because of that presence, it turns out there are some trivial zeros that this function has, and they are at the negative even integers. Okay. All right. So some of you might know this very famous equation, that the sum of the positive integers equals negative 1/12. I think on YouTube there are probably a dozen or so videos explaining this. Probably some of them explain it exactly in the way I'm about to explain it. But if you don't know this, it isn't quite true that the sum of the positive integers isn't positive infinity and turns out to be negative 1/12, but it isn't quite wrong either. So I like telling this story because we made a film about Ramanujan, and among the many things that he did, he made this audacious claim in one of his enigmatic first letters he wrote to G.H. Hardy, and I quote from this letter, "Under my theory, 1 plus 2 plus 3 plus 4, ... equals negative 1/12. And if I tell you this, you will at once point out to me the lunatic asylum." I like this quote because who talks like this today? And it is crazy at first glance, but of course to Hardy this would have not been crazy at all. So in the context of everything I've just described, how do we view this? Well, here's a proof, and I've showed this to you earlier. When we summed up the reciprocals of the squares, 1 plus 1/4 plus 1/9, ... that was the number zeta of 2. The 2 represents the squares. And that's well known to be pi squared over 6. If we just pretend and declare that zeta of -1 should be the sum of the positive integers in order, which is where we really shouldn't be declaring that, but let's pretend. If we allowed zeta of s to be summation 1 over n to the s, if s is negative 1, then formally this is what you would get. And of course, what Riemann noticed, why did I put Riemann there? Okay, in any event, what Riemann noticed in his functional equation is that zeta of -1 and zeta of 2, because 1 minus a negative 1, that's what comes up in the functional equation would be 2, are related in this way. But aha, zeta of 2 is pi squared over 6. I've got a pi squared here in the denominator, and you can carry out the calculations with sign and discover that, lo and behold, you get out a negative 1/12. So of course, from Hardy's perspective, that would have been brilliant because very little else in those first few letters that Ramanujan wrote to Hardy offered evidence that Ramanujan knew anything about proper analysis. Okay. All right. So what is it that Riemann had in mind in his famous 8-page paper? Well, I don't know that he could have graphed this, but he understood the importance of the values of this function in what's called the critical strip, and more importantly, he understood the value of locating the non-trivial zeros, and I'll get to that in a moment. But if you were to graph the zeta function, now as we have now defined it, where the real part is a half, that's fixed, and only graph it in t aspect, so the imaginary part is walking up from the origin up to about imaginary part 50, you'll get this beautiful spiraling curve. What does it mean for the zeta function to be 0? Well, of course it means it's going through 0. And there are many beautiful pictures that you can steal from the internet, because I don't have the skills to produce them myself, that illustrate the rather remarkable properties of this function. And this is just one particular aspect that is of interest to us. So what I'd like you to note is zeta of a half is something like negative 1.460354. So I think that's believable based on this graph. And graphing up to t equals 50, you encounter the first few zeros, as you see. And now I think it's appropriate to revisit what Riemann's conjecture is that all of the non-trivial zeros, apart from the negative evens, will be the zeros that are encountered along this path if you're spiraling forever. All the zeros would have to be encountered in this way. Some of you might recognize this picture. I think this is Dennis Hedgehall's writing. So there's a famous image of the location of the zero. So if you were to consider the zeta function on the complex plane between 0 and 1 for the real parts, the first few zeros are here. They coincided with what I showed you in that red graph. And there are no other zeros certainly up to that height. And that's been known for quite some time. So Riemann made this proposition, and he said it would be really desirable to have a rigorous proof of this proposition. By the way, he wrote in German, so every time I've quoted Riemann, I'm actually quoting a translation, which I assume is correct. But this is the understatement of the lecture. It would be desirable to have a rigorous proof of this proposition. So what I want to explain over the next few minutes is why it would be really desirable to have a rigorous proof and not have it be related to winning $1 million. Okay. Well, so let's just take a small step aside for a moment, and let me show you some graphs of some auxiliary functions. You can encounter many famous names in analytic number theory by just studying this question. And work of Chebyshev and von Mangold sort of illustrates how one should think about the distribution of primes. So my guess is many of you will not have seen this picture I'm about to show, but the moment you see it, you'll realize why what later became known as the prime number theorem, Gauss's conjecture, kind of had to be right. So the prime number theorem is equivalent to the statement that the limit as x goes to infinity of psi of x over x is 1, where psi of x is this very strange function. You sum up log p for all prime powers up to x, and it's the idea that every time you encounter a prime or a prime power, you indicate that, not with the characteristic function as we've done in pi of x, but you indicate that count with its logarithm. So if you've never seen this before, graph it. So every time you get a prime, you get this very, very unsmooth function. It looks something like this. So every step up occurs at a prime. But what you do notice is that this graph looks like it's doing its very, very best to hover around the line, y equals x. So I ignored ignore that. Which is exactly what the content of this theorem is, that psi of x and the line y equals x want to do a remarkable job of mirroring each other. So if that's what you want to show, you want to say, then why do the non-trivial zeros matter? And this is one way that I want to explain why it matters. It turns out that if you want to show that psi of x is asymptotic to x, you want a formula for psi of x where the main term is x. Oops, I've forgotten this is not a pointer. Where the main term is x. And it turns out that it's a famous theorem in analytic number theory that psi of x is x plus some innocuous factors, but then this infinite sum glaring in red, where you sum over the non-trivial zeros rho of the zeta function, x to the rho over rho. You see, if that red function wasn't there, the statement that psi of x is asymptotically x is literally trivial, because you can divide x into psi of x. Then you'd get psi of x over x equals 1 plus terms which rapidly decay to 0 as x goes to infinity. But there's no working around the existence of this bold red expression, and that's why we really need to know about the location of the zeros. Oh, yeah, that lowercase x is the same as the uppercase x. Yeah. Yeah, every x, there's only one meaning for x in this lecture. Should be thought of as a large real number tending to infinity. Remember, when you assemble a lecture by cutting and pasting from the internet and talks, right, these things can happen. Well, finally, the prime number theorem was established in the late 19th century by Hadamard de la Vallée-Poussin. They proved Gauss's conjecture. It is true that pi of x behaves like x over log x, asymptotically. And it's a little bit heavy, but let me just say, the proof boils down to the fact that they were able to show that the non-trivial zeros of zeta are never have real part equal to 1. All right. And that's quite a bit of work. If you've never seen that before, this is a prototype for much of what is presently done in multiplicative analytic number theory. So why does RH matter? Well, you can prove the prime number theorem, but really not be in a position to optimally use its conclusion. So for example, if the Riemann hypothesis is true, people have worked this out, you can actually bound the difference between pi of x and this logarithmic integral which is used to estimate it. In fact, it's quite good. There's a famous paper by Schoenfeld, among other things. One of the conclusions in that paper is that pi of x and li of x never differ by more than something that's roughly size square root of x, once x is at least 2,657. And compared to x over log x, which is the main term, this expression on the right is really, really small. So this idea of getting an error term of roughly size square root of x, that's kind of like the magic barrier that one is trying to approach in the subject. So if you really want to know how accurate the prime number theorem is, you want to know the Riemann hypothesis. But it turns out that the Riemann hypothesis is one of many Riemann hypotheses. There's something called the generalized Riemann hypotheses. There are Riemann hypotheses for varieties over finite fields. There's many different kinds of them. And in the spirit of this lecture, let me just restrict to the case where I'm speaking about non-trivial zeros of L functions which are morally relatives of the zeta function. And even in those cases, it's safe to say, and absolutely fair to say, that basically every deep question on primes, we would be informed if someone proved the Riemann hypothesis. It's not true that every deep problem about primes would be solved, but morally pretend that that was true. There are statements in arithmetic geometry related to the distribution of ranks of elliptic curves, orders of class groups that are informed by L functions that are very much like the zeta function. And there would be huge advances if someone were to make deep progress on RH. If you're interested in quadratic forms, Manjul-Bhargava, together with, God, I've forgotten his name now, so I feel really bad about this. I hope he never watches the video. Bhargava, following up on a very famous work of Conway and Schneeberger, very good, Jonathan Hankey, if you're watching this, yeah, I'm thinking of you. So there's some very beautiful theorems by Bhargava and Hankey on what are called universal quadratic forms, which give simple tests. If you started with a set of positive integers and you wanted to know whether a quadratic form represents them all, it's a finite test. They prove that these tests exist. Unfortunately, if you want to actually effectively show how to construct all of these tests and prove that they always work, you, in many cases, still need to know about the Riemann hypothesis. Surprisingly, if we work in algebra, we don't even really know about the maximal orders of elements and permutation groups. The symmetric group Sn, as n goes to infinity, we are not very good at estimating the maximal orders, and that is a problem that is also related to the Riemann hypothesis. If you're interested in primality testing, the running time of algorithms depend on the Riemann hypothesis, and I think in many settings people just use the Riemann hypothesis and declare that it is true and is happy with that. But if you really want to be sure, that application is definitely there. So to summarize these bullet points, it's really true that thousands of results are proved assuming the truth of RH and GRH. And so any progress on that would, kind of like in the most amazing Rube Goldberg experiment, result in like thousands of conjectures, or several hundred for sure. I'd like to give you one. I'm giving a lecture here, and I like talking about Ramanujan. So I wrote a paper many, many, many years ago with Kannan Soundarajan, who's a very well-known number theorist at Stanford, on this quadratic form that Ramanujan wrote down. So here is his famous quote from 1915, I believe. Ramanujan said that the even integers, which are not of the form x squared plus y squared plus 10z squared, what does that mean? These are the numbers you cannot get by substituting in for x, y, and z ordinary integers. The even numbers which are not of this form are the numbers which are of the form 4 to the lambda times 16 mu plus 6. Never mind that part. That's easy. We know how to work that out. The most important part of this quote is what he ends up with. He says, while the odd numbers that are not of that form, it's a set, 3, 7, all the way up through 391 in his paper, do not seem to obey any simple law. So just to emphasize, let's take the number 7 on this list. You cannot obtain 7 by substituting in for x, y, and z, an integer, in x squared plus y squared plus 10z squared. And all of these numbers you can check cannot be obtained. A very famous theorem in the early 1980s by Bill Duke, and I guess together with Schultz-Pilot, Pilo, okay, said that with respect to this list, there are most finitely many numbers that complete this list. Sound and I were very interested in trying to complete this list. We were unable to do it, but with a little bit of help, and this is it's a little bit more technical than what I've written here, but roughly speaking, assuming the Riemann hypothesis for a very specific family of L functions, then it turns out that the only positive odd integers you cannot get by substituting in for x, y, and z are on this list, and this list is complete. So that's kind of an amazing statement. You don't even have to check that there are any others if someone had to offer a test. The test is here. So when Ramanujan said that this quadratic form does not seem to obey any simple law, he was absolutely right, because what is that law? It's basically this umbrella of the GRH, and that's certainly not a simple law. We wish that was a law, but there are a lot of laws. Well, let me go on. No politics. Yeah, we wish it were a law, and we wish it was a law that could not be defied, and we wish we could prove it. All right. So how about some evidence for the Riemann hypothesis? Well, the lowest 100 billion, and I think this number changes because people are computing more, but I think this is still fairly close to accurate. The lowest 100 billion non-trivial zeros, so this is ordered by imaginary part, satisfy the Riemann hypothesis. So could the first 100 billion zeros be wrong? I don't know. There's a beautiful series of papers, and I'm going to... So this is a theorem by Selberg, Levinson, Conry, and this area of research lives on. I think Matt Young told me there's a paper on the way where this number will be improved. But for now, this is definitely what I can tell you, that at least 41% of the infinitely many non-trivial zeros for the Riemann zeta function satisfy the Riemann hypothesis. I think Matt said to expect an improvement in the second or third decimal place. So this is very hard work, very hard work. There's a lot of work that's been done on determining zero-free regions for the zeta function. Well, the zero-free regions are the stuff here that isn't white. So if if we want all the zeros to be on this dashed line, it's very disappointing to see that the slope of this curve asymptotically tends to the vertical boundaries of the critical strip. Now, that doesn't mean that people in analytic number theory have not developed tools for getting around these sorts of difficulties for some kinds of theorems. If you ever hear about what are called zero density estimates and the like, there are tools that give approximations to some of the implications of RH. What about prospects for a proof for the Riemann hypothesis? This all appeared very quickly. They're supposed to appear one at a time, but I can deal with it. If you go back decades, much in the early 20th century, it turns out that Mertens was able to show that the Riemann hypothesis is equivalent to this sort of bound for the famous Möbius function. The Möbius function is a function that is a very delightful function. It's the way to detect the number 1 from all other numbers. So mu of n is 0 if n is not square free. Otherwise, it's plus or minus 1, depending on the parity of the number of prime factors. And if you compute these sums for large numbers x, you never get anything big. And despite the fact that the Möbius function is very easy to define, it's very difficult to show that this sum, mu of n up to x, is bounded basically by the square root of x. Big O of x to the 1/2 means, just think, doesn't get bigger than roughly the square root of x. The reason that that comes in naturally with the zeta function is if you were to reciprocate the product formula that Riemann wrote down and Euler wrote down, you would basically be getting a generating function for Möbius, and then there's some steps along the way that allow you to make this connection. There's a program due to Polya, which I'll talk about briefly in a moment. There are lots of ideas in functional analysis. The buzzword certainly around the East Coast, trace formulas, and many other works. In particular, Peter Sarnak is here, so Peter, I have to move on, my time is running, but there's a very beautiful volume that Peter wrote with Nick Katz on random matrices, which have implications throughout all sorts of distributional counting type problems, not only with respect to primes, but in arithmetic geometry and the like. All right. I want to briefly touch on the random matrices because what I'm going to end with in this lecture is a statement of some theorems that I can offer you. And to properly understand them, I think I need to tell you the story about Freeman, Dyson, Hugh, Montgomery, and Andrew Olidsko. So in the early 1970s, I don't remember the year, but it's very well documented, Hugh Montgomery visited the Institute for Advanced Study, and at the time he had been studying the joint distribution of zeros of the zeta function. He was very excited by some of the numerics that he had discovered. And in a conversation with Freeman Dyson, I guess in the tea room at the Institute, Dyson recognized, oh yeah, this looks like some calculations that go back to Wigner and others when they were studying the distribution of atoms with very heavy nuclei. And that's the very beginning of the subject called the theory of random matrix models for distribution of zeros. Andrew Olidsko computed many zeros for the zeta function to test their conjectures. And in very vague language, what they conjectured is much more precise than this. There's something called the pair correlation conjecture. But for today, let me just say what they conjectured is that the non-trivial zeros of the zeta function suitably normalized seem to be distributed like the eigenvalues of random Hermitian matrices. Okay. All right. So what I want to conclude with is some recent work along those lines, and I want to offer a little bit of evidence, I think new evidence for the Riemann hypothesis, and it's related to the work of Jensen and Polya. It's actually very interesting, really. Jensen, when he died in 1925, left behind notes, like someone else that I study a lot, and these notes were passed on to George Polya, who was a very famous analyst at Stanford for many years. And I'm going to refer to the papers that came out of this as the Jensen-Polya program. So this is a little bit technical, but I'll offer the real details on Friday, but it goes something like this. Jensen's idea was to study the Riemann hypothesis and a whole family of related problems by associating to the derivatives of the zeta function, the central ones, a doubly infinite family of polynomials with real coefficients. More generally, for any arithmetic function, let's say A of n is a sequence of real numbers. For every pair of integers d and n, you can construct a polynomial of degree d whose coefficients are the binomial coefficients d choose j times, well, the terms in the sequence. So what is a of n plus j? A of n plus j is the jth term after the nth term. So when I talk about shift n, imagine having an infinite sequence of real numbers, grouping together like d plus 1 numbers, and just inserting those numbers in order as the coefficients weighted by binomial coefficients. Why did he do this? Because he noticed that, at least in the case of the zeta function, when you insert for the sequence the central derivatives of what's called the Riemanns I function, he noticed that these polynomials should be what are called hyperbolic. That's very fancy language for just saying that these polynomials have roots which are just ordinary real numbers. By the way, that's not ordinary. A typical polynomial degree 50 doesn't ordinarily have 50 real roots. So these are hyperbolic polynomials are not ordinary. And the study of hyperbolic polynomials and related things, it's actually a ubiquitous idea. What did they prove? They proved, forget all this other stuff, but they proved that the Riemann hypothesis is equivalent to the hyperbolicity. Again, all the roots of the polynomials I'm showing you must be real. The Riemann hypothesis is equivalent to the hyperbolicity of this doubly infinite family of polynomials, where the sequence in question are the Taylor coefficients of a suitable renormalization of the Riemann zeta function. So gamma of n, literally think of as being the nth derivative at s equals a half for the Riemanns I function, which you might as well think is the zeta function. Well, it's actually very hard to show that a polynomial degree 1,000 has all real roots. So it's certainly going to be very hard to show that all of the polynomials in some doubly infinite family, when the degrees go to infinity, must be real. And so what was known, very little was known. So in a PhD thesis, Chas proved the hyperbolicity for when n is 0 for degrees up to 2 times 10 to the 17th. That's a finite set. In the 1980s, Sordas, Norfolk, and Varga, and Dimitrov and Lucas handled the quadratic and the cubic case with quite a bit of work. And let me say why it was hard work. If you're going to prove that these polynomials are all hyperbolic, it assumes that you already know how to compute all of the derivatives of the zeta function, and that is a very big assumption. In fact, maybe some of the experts can correct me, but I think the first proof of the positivity of the nth derivatives of even order at s equals a half wasn't even published in literature until like November of last year. Maybe that's not right, but something like that is close to right. If you actually compute these derivatives, and I'll show that on Friday, a lot of these derivatives are like barely positive. It could be like 0.30 zeros and then like a 1, 2, 3. This is an insidious function to differentiate. And for degrees at least 4, nothing was known. Even computing numerically, this was difficult. So for these reasons, I think most people would think that this is not a profitable line of research, which I tend to agree with, but it doesn't mean that we don't do it. So what is our work? This is joint work with my former students, Michael Griffin and Larry Rowland, together with Don Zagier. And our theorem is this. For every degree, not just 1, 2, and 3, every degree, d could be 10 to the 10th, any d, we have defined a normalization, a renormalization for those polynomials called j hat. And we take the limit as n goes to infinity of these, which is like taking higher and higher derivatives of the zeta function. Those polynomials actually converge to polynomials that are known and are very much part of this random matrix theory. They converge to what are called the Hermite polynomials. They converge coefficient by coefficient to the degree d Hermite polynomials. And of course, the Hermite polynomials, they are orthogonal polynomials with respect to an exponential measure, which by the theory of orthogonal polynomials means that they have many special properties, one of which is that they are all hyperbolic. And in particular, not only hyperbolic, I know exactly where all the zeros are. So the main catch here is that for each degree d, because of this limit, all but finitely many possible of the derivatives of the zeta function will have a degree d Jensen polynomial, which is hyperbolic. So I offer you this, and if we're allowed to cheat and I take boxes and take the widths of the dimensions of the boxes to infinity in a suitably but obnoxious way, I could say that we've proven 100% of these polynomials are hyperbolic, but that would be like politics today. It wouldn't be quite fake. There'd be an element of truth to it. But what I want to stress is that we've actually located the zero. So what is this like saying? So it's like saying this. There really should be quotes around the word theorem, but this is what I want certainly experts to be thinking, what this theorem says. You see, if we've proven this limit and we're able to make it effective, by the way, how does the hyperbolicity follow? These Hermite polynomials have all real roots, and they are all distinct. So if you have a sequence of polynomials that converges to such a polynomial with distinct roots, at some point it cannot be true that the zeros always have complex conjugate pairs because they don't want to double up in the limit and produce a double zero. It's just that. So what the magic is this J hat. So on Friday I'll explain how you actually compute these derivatives. We do it to arbitrary precision. You don't have the right to claim a theorem like this unless you really know to arbitrary precision these derivatives. Turns out it's not difficult to do. We have that. And then I'll explain how we get these limits on Friday. But for experts, I want to stress this. This is somehow related to the conjectures of Dyson, Montgomery, and followed by the calculations of Elitzko, is that I'd like you to think of this theorem as saying that the GUE random matrix model prediction is true for the Riemann zeta function and derivative aspect. So let me, because Peter is here, explain what I really mean by that. So the way you think about these Jensen polynomials of degree d and shift n is that the degree d shift n Jensen polynomials want to emulate the lowest lying d zeros of the nth derivative of the zeta function. If the Riemann hypothesis is true, then the zeta function lives in what's called the Pauli-Laguerre class, which is closed under differentiation. So GUE should hold for all of them. And so there is then a GUE prediction for the derivative aspect, and we show that the Hermite polynomials which satisfy the GUE distribution, which is Wigner's semicircular law, is free. Great. Anyway, this is what I want to end with. I think this is very good evidence for this body of work related to the Riemann hypothesis. We have some evidence supporting now, as a theorem, a random matrix model. And I think for people who study our work, they'll be interested in how we actually compute these derivatives. And before anyone does that, I'd like to say my PhD student, Ian Wagner, is going to be doing that to a large class of L functions, modular L functions, Dirichlet L functions, basically L functions with Euler product that are analytically continued by means of integral representation. So these theorems will be true there too. Great. Thank you very much.